examples that you might see on the basic test for target 7, which is dealing with the complex number system, the imaginary unit. So to get this in simplest form, what we need to do is we need to, first of all, take out the negative under the square root. And then we need to find a perfect square factor that goes into 80. Now you may recognize that 4 times 20 is 80. So you could change it to square root of 4 times square root of 20. But that's not fully simplified because 4 goes into square root of 20. Or 4 goes into 20 again. So you want to find the biggest one. So if you do 16 times 5 is actually 80. So I'm going to change square root of negative 80 to square root of 16 times square root of 5 times square root of negative 1. And then what I would have is the square root of 16 becomes 4, the square root of 5, and the square root of negative 1 is I. That's the imaginary unit. So then I just multiply these together. Negative 3 times 4 is negative 12 times I times square root of 5. I always end with the square root with the radical just because anything after the radical might appear like it's underneath the radical. So those are probably the toughest type into the basic part. The adding and subtracting complex numbers, remember a complex number is a number that's in a plus bi form. It has a real part and an imaginary part. So the real part here is 3, and the imaginary part is negative 7i. So I have two different complex numbers, and I'm subtracting them. And in order to do this, all you really do is add or subtract the like terms. But the place where you might make a mistake on this is when you're subtracting, you have to remember to distribute that subtraction. Or think of that as plus a negative. So it's really 3 plus a negative 7i. I could keep change on that as well to change it to plus a negative. Plus, now I distribute the negative to the 8, and I distribute the negative to the minus 9i. So what I end up with is a double negative, a minus a negative 9i. So that's a common mistake. People will have a minus 9i, but it's really positive. So then we just combine our like terms. 3 plus negative 8 is negative 5. Negative 7i plus 9i is 2i. So that's how you add or subtract complex numbers. You just add or subtract the like terms. And then the third type under the basic level is multiplying complex numbers. So there's a few ways you could do this. You could use the distributive property twice. You distribute those two, the 2 to those 2, and then you distribute the negative 3i to those 2. You could also remember that as FOIL, first, outer, inner, last. Or you could use a visual box method to multiply those out. So the box just shows you how to do that multiplication. So when I'm distributing the 2, it'd be 2 times negative 4 and 2 times negative 5i. And then I'm distributing the negative 3i. Negative 3i times negative 4 is 12i. Negative 3i times negative 5i is a positive 15i squared. Now this is another big thing that we have to remember. I squared is square root of negative 1 squared, which is negative 1. So the value of I squared is actually a real number, negative 1. So 15I squared becomes negative 15. And then you just combine the like terms. So we have negative 8 and negative 15 combined to negative 23. That's the real part. 12i and negative 10i combine to 2i, and it's a positive 2i, and we always put real part plus imaginary part in that order. Now moving to the next page, we have more of the meets type level. So it's a little trickier when we're dividing, because the rule here is you cannot leave a radical in the denominator in simplest radical form. And I is a radical. I is the square root of -1. And for those of you in your Chromebooks, if you could close those, please. Sorry, I forgot to remind you of that. So if I have an I in the denominator, what I'm going to do is I'm going to multiply by I in the denominator. That will turn that I into I squared, which is -1. So it won't be in the denominator. But I can't just multiply by anything I want unless I also multiply the numerator by the same thing. So what I'm doing is essentially multiplying by I divided by I, which is 1, because anything divided by itself is 1. So the denominator is going to be -14 times I. And then the numerator, I'm going to distribute the I to both of those. Notice how there wasn't parentheses around the complex number to begin with. But if I'm multiplying a complex number by something, I have to distribute that something, in this case I, to the real part and to the imaginary part. So it's 18 times I minus 5 times I times I. So then what I'm going to do is I'm going to change my I squareds to -1. So if I squared is -1, this becomes 18 minus 5 times -1, which is 18 minus a -5, which becomes 23. And on the bottom, it's -4 times -1, which becomes +4. So the answer to this is actually a real number. There is no imaginary part. Oops. Oh, I'm sorry, there is. I made a mistake, didn't I? Because this should have been I.
Yeah.
So now I can't combine that. So my numerator would just be 18 plus 5, 18I plus 5, and my denominator would be 4. So then I simplify that by distributing the divide 4. So I get 18I divided by 4 plus 5/4. Switching the order there, put the real number 4 first. So that's going to be 5/4 is the real part. And then the imaginary part, I'm going to reduce that fraction. 18/4 reduces to 9/2. And there's my final answer. Now with number 5, I have to do something similar, but I have to get the I out of the denominator by multiplying by what's called the complex conjugate. And the complex conjugate is the same thing as the denominator, except in the opposite sign between them. So if it's a plus, change it to a minus. If it's a minus, change it to a plus. And once again, you have to do that to both the top and the bottom. Okay? So I'm going to make a little box for the denominator. And this kind of shows what happens when you have complex conjugates. So I have 2 and 3i and 2 and -3i. 2 times 2 is 4. 2 times -3i is -6i. 3i times 2 is +6i. And 3i times -3i is -9i squared. And -9i squared, because I squared is -1, becomes a +9. So then 9 and 4 are the real parts, which become 13. And the imaginary parts are 6i and -6i, which cancel. And that's why we multiplied by the complex conjugate, because the imaginary parts will cancel. But then we have to do something similar in the numerator. So I'm just going to put it down. So I'm multiplying this. I'm going to put it down here. I'm going to make a little box. You don't have to do the box. You could use the distributive property. 1 plus 4i times 2 minus 3i. So I get 2, negative 3i, 8i, and negative 12i squared. And that I squared term is negative 1, so negative 12 times negative 1 is positive 12. So I have 12 plus 2, which is 14, and then 8i and negative 3i is 5i. And just distributing the divide 13, written in complex number form. Notice I put the 5/13 times I. You could also put the I in the numerator with the 5. All right, so this little bit goes up here. And then the last one on this page is just kind of combining all that together. So the first thing I'm going to do, doing order of operations, is I'm going to do exponents. So I'm going to square negative 4 minus 5i. You cannot just square this and be done. It doesn't work that way. You have to think of something, a binomial squared, as negative 4 minus 5i times itself. So we get 16, 20i, 20i, and 25i squared, which again becomes negative 25. So this part that we're subtracting from 2 minus 3i is going to be, I'm putting it in parentheses because it's whatever we get when we simplify this. It's going to be 16 minus 25, which is negative 9. So I'm looking over here and I'm subtracting the real parts, plus 20i plus 20i, which is plus 40i. And now I'm going to distribute the subtraction, so it's really minus a negative 9 minus a 40i. And I can combine the real parts. 2 minus negative 9 is 11, because we change that to plus a positive. Negative 3i minus 40i is negative 43i. So there's the complex number that represents the simplified version of that. Now, as far as one more thing that we did in Target 7 yesterday, we graphed complex numbers. And this is really pretty simple. You're just going to graph the imaginary part on the y-axis and the real part on the x-axis. So negative 2 plus 3i has a real part of negative 2, and the imaginary part of the complex number is 3i. So from the origin, I'm going to go negative 2 on the real axis, which means I go left 2, and positive 3 on the imaginary axis, which means I go up 3. Oops, right there. And I'm just going to put a point. And that's it. That's the graph. Just a point. Now, we did take it a step further yesterday, and I said, what is the absolute value defined as for a complex number? So if you're asked to find the absolute value of a complex number, all you're going to do is find the distance from the origin to that point. And you could use the distance formula, where what I prefer to do is to do a right triangle. The legs of the right triangle would be 2 and 3. So using the Pythagorean theorem, a squared plus b squared equals c squared, c is going to be the square root of 2 squared plus 3 squared, which is the square root of 13. Now there's one more here that we didn't do. This is kind of actually a tease into the next upcoming target in the next unit. Finding the zeros. Remember the zeros of a quadratic equation, which is what we have here. This is actually in vertex form, if you recall. The vertex would be 4, 25, that point. It's going to be a parabola that opens up because this is positive. The zeros are the x-intercepts, which are the values that make the function equal to 0, or make the y equal to 0, more specifically. So if I put 0 in place of the y, and then what I'm going to do is I'm going to solve this for x. And this is actually a lead-in into the first part of target 8, which is solving a quadratic equation like this using square roots, which we did a little bit already in target 2. So I'm going to undo with the reverse order of operations. I'm going to undo my addition first. And then I'm going to undo my exponent. And this is the key. We undo that exponent by square rooting. But we have to remember when we do that, when we cancel a square with a square root, we always get plus or minus. And then the last thing I do is I undo what's in the parentheses, which in this case is subtracting 4. So I would add 4. So this is what my answer looks like. X equals plus or minus whatever the square root of negative 25 is, plus 4. Well, we know what the square root of negative 25 is. The square root of the square root of positive 25 is 5. So the square root of negative 25 is 5i. Because square root of 25 can be thought of, negative 25 can be thought of as square root of 25 times square root of negative 1. This is 5, this is I. And then we have our plus 4. Normally, since this is a complex number, we would write our answer like this. Real number first, plus or minus 5i. Which means two answers. They are complex conjugates. It means one answer is 4 plus 5i. The other answer is 4 minus 5i.
We can move right to the top there.
Yes. That is a complete review of what we learned yesterday.